Hi, everyone. Thanks for coming. My name is Dylan Carney. I'm an engineer on the traffic team at Stripe. And I'm here today to talk to you about some things that my team built with Envoy over the past year or so. I'm going to talk about what we built and how we incorporated Envoy into what we built, some of the challenges we faced along the way. Maybe some of them are interesting or novel, depending on your experience with Envoy. And then with the benefit of hindsight and looking back at the entire project, what were some pros, some cons, maybe some things we would have done differently. So with that, before I dive into any sort of technical details or just start rambling on about HTTP or Envoy, a bit about my employer, Stripe. Some of you might be developers in the audience. You might have integrated with Stripe at one point, or you might work for a company that uses Stripe. I know I saw it up on a slide earlier. But Stripe is a technology company that builds economic infrastructure for the internet. So what does that actually mean? Another way to think about that is that we run software and APIs to accept payments and to allow companies to manage their businesses online. So a large part of that is removing the complexity of global money movement. So we have millions of customers in over 120 countries that use Stripe to start, run, and scale their business. So what we have here is a pretty abstracted, high-level view of where some of those 120 plus countries are located. And you'll see that we, as the title of my talk alluded to, literally span the globe. Now, I'm a software engineer. I'm sure a lot of you are as well. And anyone who's been in the software engineering or computer science fields for a while knows that the field is littered with problems to work on. Some of them are maybe a little more interesting than others, depending on your background. We have problems of resource constraints. We have problems of taming overwhelming complexity. But I would argue that having millions and millions of people all around the world who want to use your software all day, every day, with many nines of availability, is one of the greatest problems to have. It's fun to work on. It turns out from a business perspective, it's also a pretty great problem to have, as you can imagine. So that's the problem that I want to talk about today and how my team at Stripe overcame some of the inherent obstacles with that particular software engineering problem. Oh, sorry, I didn't even read my slide here. Another way of saying that is with increased reach, with global reach comes some pretty interesting software problems. So the first one is a basic tale of latency. It's a fundamental problem when dealing with networks. Now, if we look at the time it takes some data to make its way from Seattle, where I live and where I work, to where we are today here in San Diego, we're looking at, I don't know, depending on your source, about 36 milliseconds. Now, if we move that out to a city I was recently in, Mexico City, we're now looking at, say, 67 milliseconds, give or take a few. But if we move further afield and look at parts of that globe that I showed earlier, much farther from Seattle, like Mumbai, say, we're up to a pretty appreciable 275 milliseconds. I don't need to beat you over the head with examples for you to get the point that some places are much further away than others. The speed of light is a constant. It's not moving any faster. Mumbai is not getting any closer to Seattle, last time I checked. So one way you might think of to combat this, it's not just a naive solution, but one that actually works pretty well in practice, is to move some of your computers closer to where those users are. It makes intuitive sense, and it makes fundamental physical sense as well. So that's exactly what we started to do at Stripe and what my team initially worked on. And what we ended up with is this is a vastly oversimplified network diagram. But we moved some of our computers closer to where our global users are. So for the sake of argument here, I've chosen Japan, Ireland, and the US, mainly for the reason that they're all far from each other. And again, for the purposes of argument, I have sort of our home data center and maybe all of our databases located in the US. Now, the significance of the different colors on the arrows, the red arrows represent traffic that moves over a connection that might be the user's internet, say, a mobile network, their home broadband, their office, what have you. Whereas green arrows represent connections or traffic over connections run and operated by Stripe. That'll become kind of important in a second here. So great. We've established points of presence, or POPs, as I sometimes refer to them, in places all around the world. They're closer to users. Well, what does that buy us? The first thing we can do is drastically reduce the TLS negotiation time. So any good API is going to require that you establish a secure TLS connection before doing anything else. And if we remember real quick, back to maybe our computer networking classes we took in school, we know that just to set up that TLS connection, before we can do anything else, we have to do a bunch of round trips. So between the sender and the receiver, we have a full round trip, just to open a TCP connection. We've got 2 more to exchange cipher suites and set up TLS, et cetera, et cetera. This is all before we can exchange any meaningful application data at all. Now, TLS 1.3 and things like that have some mitigations to make this faster, but those aren't widely adopted yet. And so we see that we've paid a pretty large cost already if we're talking about the sender and receiver being located in places like Seattle and Mumbai. So how does Envoy help with this, right? I just talked about TLS negotiation over a user's internet connection. Well, after that TLS connection is established, we still might have to do something like this. We still need to get that user's API request all the way from wherever they happen to live through one of our points of presence, all the way back to where our home data center lives. We might need to hit the database for that, and maybe those are only geographically located in one place. Now, again, there's nothing about this, the part that Envoy can help us with is making that leap from 2 geographically distant points. Japan, Ireland, those places aren't getting any closer to the US no matter what fancy tricks we wish we could pull. So in order to talk about the Envoy portion of this, I'd like to zoom in on the most interesting part of this topography, which is, again, the links between geographically distant locations. So we can ignore the user's internet, we can ignore our database, and focus on these links. Now, what we did at Stripe is we connected all of these points of presence using MTLS HTTP2 connections. So MTLS is just mutual TLS, so both sides authenticate each other. That gives us security for all these connections. And HTTP2, we'll talk about some of the cool features of HTTP2 in a second, but suffice it to say it gives us efficiency, the ability to multiplex connection or requests over a single TCP connection, and solve some of the like head-of-line blocking issues you may have heard of with HTTP 1.1, where in order to execute n requests, you first do the first request, wait for it to complete. Do the second request, wait for it to complete, et cetera. With HTTP 2, we can multiplex these and perform them more quickly. So the great thing about setting up this pretty basic Envoy use case is by having Envoy manage the connection on both sides, those connections, which are pretty expensive to establish, you can imagine. We've got to do MTLS, between faraway places. Those connections now outlive any application restarts on either side. So at Stripe, we deploy many times a day, dozens of times a day, depending on the day. If we have to deploy to any of those points of presence and restart some servers, we don't have to tear down and reestablish these MTLS backhaul connections, as we call them, to kind of steal a metaphor from the trucking industry. Those connections stay established and quote-unquote warm so that any incoming customer requests, whether it be to Japan, Ireland, the US, what have you, lands on one of those connections and gets sent back to our home data center. So what Envoy has done here is drastically reduce the overhead of serving each new user connection that comes in. So that's great. We, as you can imagine, connected all of our data centers in this way. Another thing I want to touch on real quickly is something we built with great help from Envoy, which is our blue-green deployments. So a quick primer, if you're not familiar with what blue-green deployments are, conveniently I've duplicated our home data center, made one of them blue, one green. They're two identical sets of infrastructure, and typically in the steady state, you have 100% of your traffic on one copy, let's say blue. That leaves you free to deploy new software to your other copy, the green copy, and then shift traffic at your leisure to test things out, make sure everything looks good, there are no bugs, and you can gradually ramp traffic to your new software version, maybe something like this, until eventually you're free to deploy back to blue. So that's blue-green in a nutshell. Well, the great thing about using Envoy for this is that we use a custom XDS sidecar that is hooked up to a developer CLI. So any developer can easily and quickly define that traffic percentage and that ramping and have it reflected in Envoy across all of our data centers incredibly quickly. The other nice thing that gets you is that since we're using Envoy's software-defined networking for this, rather than like changing weights on a DNS entry or changing DNS entries altogether, we don't have a long tail of traffic that refuses to shift like you sometimes get with DNS. Clients love to cache DNS entries and not resolve them when you want them to. So the joke we use at Stripe is we use Envoy SDN, not DNS, to shift this traffic. It's easy, it's quick, we get complete traffic shifting, it's easy to audit. And again, it works dozens of times a day for us. It's probably happening right now as I speak. I'm sure my teammates are back in Seattle deploying like mad as we speak. So these are all elements of what we think of as our custom control plane that we built at Stripe using Envoy. So we have custom XDS services, like I said, that give us control over routing, traffic ramping. They power all of our blue-green deployments instead of DNS and its myriad issues. And using the priority and locality features of Envoy's configuration, we've been able to establish different tiers of failover infrastructure. So through both active and passive health checking, we allow Envoy to fail over to different classes of infrastructure if it detects problems much faster than any developer with their own cool little CLI would manually be able to shift traffic in an incident. And we can do cool things like prefer nearby infrastructure versus infrastructure further away, which is the locality piece of that. Again, because we have developer tooling built up on this, we can manually remediate incidents pretty easily. We can shift traffic off of defective hardware, bad deployments, et cetera. We can also and do take advantage of Envoy's header-based routing and things like that to not only route specific requests to particular infrastructure, but requests, say, per customer or per account. And I believe there's a talk coming up later today about some dynamic routing that I'm excited to hear about. Of course, it wouldn't be a comprehensive talk if all I did was talk about the great things we built and none of the challenges we experienced along the way. So I mentioned earlier that HTTP2 allows you to multiplex many requests onto a single TCP connection. So what we have here, I know there's no y-axis and there's no numbers on here. That's on purpose. But this is a chart from our production infrastructure between two of those geographically distant points of presence. Let's just say Ireland and the US. And what we're looking at is the number of HTTP requests per TCP connection over time. So you'll notice there are two of them that seem to be a lot busier than the rest. And this is a pattern we actually observed when we started building this infrastructure. Now we run multi-threaded Envoy on the server. We have one worker thread per core. I think you know how this story goes. Envoy defers to the kernel for certain things like figuring out which worker thread will accept an incoming connection. And we found in our initial configuration that busy threads tended to win. So connections with many requests tended to accept new requests. So with this knowledge in hand, and again, going back to HTTP2, which is handling data for multiple requests at the same time, that's known as a stream in HTTP2 parlance. Here in this example, we have data for streams 1, 3, and 5 all being sent over the same TCP connection. By the way, these images come from the great high-performance browser networking book that's freely available online. It's amazing if you deal at all with HTTP. So for Stripe, this means we could have requests for, say, one of our smallest startup customers. They're just trying to charge a credit card to make a few bucks to keep the lights on. Right alongside requests from one of our largest, most important enterprise customers, those customers that rely on us for those many nines of availability and uptime. So why does any of that matter? Who cares if more requests are on one connection or the other, as long as they're succeeding, right? Well, as we know, or we should constantly remind ourselves, the network is not reliable. That's a fundamental fact. And we experience, especially when going to these geographically distant locations, bad network conditions, things like TCP packet loss. So again, quick primer, packet loss and TCP retransmits are what happen when data gets lost in transit. So if we send 3 TCP segments, the receiver only gets 2 of them. Eventually, the fact has to be communicated that, hey, I didn't get one, retransmit it. This happens all the time. TCP is pretty good at dealing with this. But again, what happens in practice when packet loss and retransmits start to occur? Well, I apologize if this is a tiny bit hard to read in the back, but what we're looking at here is a blue line going steadily up and to the right, and that represents TCP retransmits. And this is from our production infrastructure. And so we have cumulative retransmits. That means things are having to be resent over and over by the operating system. We're experiencing some sort of network difficulty. And the green line is a measure of the kernel's write queue, so the data backing up that's unable to be sent over the wire during that time of retransmits. So this kind of makes intuitive sense, right? Like retransmits are happening, the kernel's like backing up. For the customers, that means increased latencies, timeouts, things that are not great. So this next chart, I've kept the green line, the kernel write queue. What we see instead, the blue line is now a measure of the effective bandwidth of that connection. Again, intuitively makes sense when the retransmits and write queuing are happening, bandwidth decreases dramatically. So one thing we did is we changed which congestion control algorithm we were using on the hardware that I diagrammed earlier. We used a new congestion control algorithm called BBR. This is something that came out of Google Research, I believe. And what the silly chart here attempts to kind of show is that BBR attempts to maintain higher throughput in the face of packet loss, retransmits, network instability. However, rolling this out was not a simple upgrade for us. It depends a lot on your OS version, your kernel version. Might not be the easiest thing to roll out. We made some other tweaks once we set this up. So in addition to changing the congestion control algorithm, we encountered this HTTP2 head-of-line blocking problem. Well, HTTP2 is supposed to solve head-of-line blocking, but it has its own head-of-line blocking problem. It's just one based on TCP. If TCP isn't able to send all the packets, there's nothing a higher-level protocol like HTTP2 can do to fix that. So one thing we did is we increased the number of upstream TCP connections. And what we found is that that distribution of requests per connection got much more even. And we didn't have the disproportionate impact when one link would experience packet loss or retransmits. And we did this by telling Envoy to use these upstreams. So as it turns out, this isn't actual Envoy config, as you can tell, but Envoy is more than happy to open twice as many TCP connections to foobar.stripe.com if we tell it to. So this was a little unexpected, but it was great because now we have the best of both worlds. We have HTTP2 request multiplexing, so we get more requests per connection, and now we have more TCP connections. Great, we're getting somewhere. We're now sharing that request burden evenly across our connections. It's a little bit of a, I guess I'll call it creative solution. It felt weird to set something like this up in config, but again, Envoy is more than happy to honor it. So with enough custom tweaks like this, we eventually figured out that we could manage the bandwidth and request burden across all of our geographically distributed links, and the infrastructure became stable. So this is kind of where we move into the pros and cons, looking back, what would we do differently part of the talk. So again, BBR congestion control was something we used, along with the FQ, fair queuing, packet scheduler. These are all things I don't have time to dive into. We also enabled TCP keep alives on all of our upstreams. Depending on your cloud provider and what middle boxes you might have in your architecture, this becomes pretty important to not have connection state get garbage collected out from under you. We can, if you find me later, we can talk all about the fun problems that come with that. So let's look back. We built this architecture. What were some of the things it bought us? So the biggest set of pros is that we have these backhaul connections, as I referred to them, that outlive our application process restarts. They allow us to efficiently send incoming customer requests all around the globe without paying this massive setup cost for each additional connection. We have great observability now between all of our network links and our data centers. Again, the running joke, any conversation at Envoy about Envoy that happens at Stripe usually starts with, oh, there's a metric for that. And indeed, there literally is a metric for almost everything. So we have great observability now. Again, fixes get propagated to all of our network links between data centers roughly at once. I don't want to say at once. Whether they be fixes for a CVE or regular Envoy version updates. This is in contrast to having to upgrade and migrate all of your applications at each of those points. And similarly, network behavior. So you find a better configuration, a better way to do retries. You want to change the cipher suites your TLS connections are using. You can change that behavior across your network topology without having to go modify 100 applications. Now, I'm a software engineer. Again, I write application code for a living. Why do I make it sound like changing an application is this insurmountable, huge pain in the ass task? Well, it's because teams, not only at Stripe, but every company I've ever worked at are polyglot. So at Stripe, we have people writing servers and applications in Go. We have a ton of stuff in Ruby. We have some Scala thrown in there. But even within a language, you have different frameworks. People might be using different network clients. You might have different runtime versions, et cetera, et cetera. All of those are going to have different network behavior defaults, different ways to configure things. And so making a sweeping network behavior change across many services, languages, frameworks, clients, indeed ends up being a huge challenge. So we decided to sort of outsource that to Envoy, where things are much more uniform. Again, I can't give pros without giving some cons. So what are some cons that we get with the benefit of hindsight? So one is that having Envoy manage both sides of every connection between every data center adds a lot of moving pieces to your stack. All those pieces need to be monitored. They need to make their way into your network diagrams. They need to be upgraded from time to time, and your engineers need to learn about how those pieces work and how to operate them. So they need to know where the knobs are. How do I change config? How do I go about manipulating Envoy in practice? Things like timeouts and access logs and vestiges of network behavior that live in your app still need to be kept in sync with Envoy. That's kind of a minor point. A bigger one for us was when you encounter bugs in a product like Envoy, it might not be in the sort of wheelhouse or domain of your application developers. So for us at Stripe, there were a few things we wanted to work on in Envoy, and it turns out we don't have a lot of in-house C++ experience. Envoy is a large C++ application. So that was just something to think about. Again, you have to spread operability knowledge amongst your team members. I'm not on call right now, thank goodness, but when I am on call, I need to know how to operate all the pieces of the stack I'm responsible for, whether that be Envoy or any other piece of software. And I see that I'm running a little low on time, so I don't have time to dive into this last one, but it's pretty interesting if you want to find me after. The actual implementations of the HTTP protocols themselves might differ slightly in Envoy than they do in other pieces of your stack, whether that be Nginx, Go, HA proxy. Now you're thinking, well, HTTP is a standard. Everything works the same if it's codified in a standard. Well, yeah, most of the time. And again, I have some fun stories about that. I picked Nginx, Go, HA proxy. These are common at Stripe, common other places. So I guess that's a lot of information. I apologize. I just kind of beat you over the head with BBR, TCP retransmits, Envoy configuration, XDS sidecars, a lot of jargon. But the message I'd like to leave you with to kind of wrap this up is that we built a network topology heavily based on Envoy, and we did indeed span the globe. We used Envoy to connect those millions of customers in those 120 plus countries. I'm sure I left some of them off of this diagram. And we allowed people to transact, move money, start, run, and manage their businesses online 24/7, not many nines of availability, and they're doing so even as we speak today, maybe for some of the businesses that employ all of you. So we couldn't have done it without a lot of help from the Envoy community. I actually just met someone before my talk started that I knew from working on a PR with. I'd never met her in real life. I was like, oh, wait, I know your GitHub username. So thanks to everyone out there who has worked or helped make Envoy what it is today. And with that, I have 37 seconds. So thank you.